Hi. So in this first video, we're going to start by introducing just the basics of radar. And what I want to start with is talking about how radar works in terms of just transmitted power and introduce you the radar range equation, which allows us to calculate what the expected power of the received signal is from a radar system. So let's start by just kind of reviewing what a typical radar configuration looks like. Every radar system needs to have a transmitter and a receiver. And there's some antenna, which is connected to the transceiver, which allows us to transmit electromagnetic waves into the atmosphere. It will interact with the atmosphere. And quite literally, I mean interact, because it's possible to have precipitation and other sources of attenuation in the atmosphere, which affects the received power ultimately. But once it propagates through the atmosphere, it's going to backscatter off of some target, and then it will come back through the atmosphere to your antenna. And once you get your received signal, you'll usually have some hardware on the received end, which is geared around trying to, isolate and eliminate sources of noise. Usually you have filters so that you're only receiving and preserving the signal around your bandwidth of interest. And then eventually you digitize your signal and it goes to some signal processing unit, which can either be an edge computing device or it can be your laptop or something of that nature. So there's several different types of topologies in general with which radar systems can operate. If the transmitter and receiver are co-located, and this is the situation that you'll have in pretty much all of our radar systems in the lab, where you have a board that has, the antenna will serve for both transmission and receiving. Or you'll have to, for FMCW, you'll have a separate antenna for transmission and reception, but they're co-located. So this is known as a monostatic radar configuration. In contrast with what you would get if you had a bistatic radar, where your transmitter and receiver are located at different locations. When later on we talk about target detection, you'll see that the position of the transmitter relative to the receiver actually does have an important impact sometimes on our ability to be able to detect targets. Then there's the more general multi-static radar case, which is what you would have if you had multiple transmitters and multiple receivers that are all located in different locations. And sometimes this is also known as radar networks. Sometimes you have different topologies and architectures for this, depending on the type of radar you have at each node. But in general, the radar community will call this a multi-static radar. So in general, what comprises our received signal when we look at what comes back in the backscatter? You're going to get a superposition of several different components. The electromagnetic wave will interact with everything that it actually touches and bounces off of. So this includes both the ground as well as the target. Reflections from objects or surfaces that we're not interested in, such as, the ground, it might be, the waves in the ocean, or any kind of particulates due to weather events and so forth. That's more generally known as clutter. In contrast with the reflections from the object that we're interested in, which in general we'll call a target, regardless of what application we're using it for. And when we think of target echoes, there's two different types of target echoes that might be in our signal. One is known as kind of like your direct path target echo, which means that the transmitted signal bounces off the target and directly comes back to your receiver. Or the multipath case, which is that after bouncing off of the target, maybe it bounces off a bunch of other surfaces and then comes back to your radar. Generally speaking, multipath signals are much weaker than the direct path signal. And so when we talk about trying to do target detection, we're almost exclusively in most cases trying to consider the case where we're trying to detect the target based on the direct reflections back to the receiver. However, in recent years, there have been some interesting applications of trying to do multipath based detection, which has led to the emergence of the concept of non-line of sight radar or detection around the corner and things of that nature. But again, for the purposes of this tutorial, we're primarily going to be concerned with detecting the direct path signal. Now, in addition to target and clutter reflections, we may also have some noise. Oftentimes, this is due to noise in the electronics of the radar system itself. So we're dealing with things like shot noise, thermal noise, and so forth. There may be also some, external sources of noise, if you think of things like cosmic noise, but, usually most of the internal noise we'll be dealing with is going to be from our system itself. But there may be other sources of electromagnetic signals in the environment, and this is something that our received antenna will also pick up if it's in the right frequency range. And that includes things like jamming. If you have like a situation where someone's explicitly trying to kind of mess up your signal, then you may have jamming signals that you need to take into consideration. And there may be other sources of electromagnetic interference, such as communication signals, television station, the RF emissions from television stations, and so forth. And so actually one of the more important problems of radar signal processing and radar design in general is how to design radar systems so that they can coexist with communication systems, and how do we mitigate sources of interference, especially when we consider applications like automotive radars, where there's radars everywhere around you, right? Nowadays, all cars have radars. So let's start by considering how we can first model and represent the expected, the power of the expected backscatter of the radar. And I want to start by considering just like what's known as an isotropic antenna. An isotropic antenna is an antenna that transmits equal power at every single point, regardless of the angle. So you can think of, anywhere on the sphere, you're going to have the same power that's being transmitted. So the total power of the transmitter is power PT, and therefore, if we consider that the surface area of a sphere is 4 pi r squared, we can calculate the power density at a distance r, more commonly known as the range r, as PT divided by 4 pi r squared. Now, most antennas are directive, and usually there's a parameter called the antenna gain, which really tells you how much the antenna itself is kind of boosting this nominal, isotropic power density. So we're going to multiply the power density by G just to reflect the amount of boosting due to the antenna gain. Next, we need to think the target scattering. So if you kind of expand the sphere out until the range R, which is the distance that the target is to the radar, then we now need to consider how much power is being backscattered by the target. This is more broadly known as depending on the radar cross-section. The radar cross-section has the symbol of sigma, and it has dimensions of area, typically meters squared. And usually what we can consider just kind of nominally is that sigma multiplies with this power. So it's kind of like, usually it's going to be less than 1, and it's going to multiply into the amplified power density that we're talking about. And again, if we consider that the backscatter is potentially isotropic. Now, this is a huge approximation, right? Like typically the backscatter from an object is not going to be the same in every angle, but for just these initial purposes, we're going to consider that it is such. And because of that, we're going to divide by 4 pi r squared again. And what this will do is it will tell us how much of the backscattered power is coming back to our antenna, which is again a distance of r away now from the target. So once we get the backscattered signal back to our radar transceiver, the next question is how much of this backscattered energy is actually being acquired by the radar antenna. And the way that we can consider this is by defining a parameter known as the effective area, which kind of tells you what the ratio of the actual power is being acquired by the antenna. There is a kind of a design rule, which, I do have a derivation of, and I can kind of show you where it comes from, kind of independent of this tutorial. But in general, we can show that the effective aperture AE is related to the antenna gain by 4 pi divided by lambda squared times the effective aperture. Lambda squared here is the wavelength, which is related to the frequency of our transmit signal. So if you take this expression for the effective aperture and you plug it back into the equation and combine terms, then you can get the equation that we have here at the bottom of the slide. Now, there's one other factor that we need to take into account, and that is various terms of losses. In the beginning, I talked about how the atmosphere can have certain effects on the received backscatter. And so there is some amount of atmospheric losses. A kind of rule of thumb or initial design equation that we can use to try to model atmospheric propagation losses is shown here on this slide. Alpha represents the amount of attenuation that we get in decibels per kilometer, and R is our distance in meters. To give you an idea of how much of an effect it can have, if you look at the chart that we have here on the right, you see how much the attenuation is as a function of frequency. And you'll notice that as the frequency increases, there's a general increasing trend of the attenuation. This is something that's important to keep in the back of your mind because, we have a wide different range of radar frequencies. If you want to have greater penetration through materials, and if you want to have longer distance detections, then you'll use low frequency radar systems. But a lot of times there's applications which are nowadays in the millimeter wave, like 77 gigahertz. And the higher in frequency you go, the more the impact of the atmosphere is going to be in terms of reducing the power of your signal. And therefore, your ability to detect targets is going to go down with distance. And so usually you'll see that short range radars have these very high frequencies. But if you're trying to do kind of long distance radar applications, such as either, like, for example, remote sensing applications, such as like ice sounding and things of that nature, then you're going to get really, really low frequencies according to what you need to be able to also penetrate the material and penetrate the ground. This is just kind of zooming in on that figure for you so you can kind of take a look at it more closely. It's kind of an interesting chart to take a look at. And then, obviously the weather conditions also affect. Now, one of the great benefits of radar in contrast with other sensors such as, LiDAR or cameras is that relative to optical sensors, radar is relatively unaffected by weather conditions, fog, haze, etc. But that does not mean that there's no effect at all. There is an effect. It does weaken your signal, but of course not to the point where you can't see anything at all. And this chart kind of gives you something that where you can see how much attenuation there is in terms of dB per kilometers for different kind of rainy conditions. So if we take all of these factors together, then you can see the equation here in the yellow box. This is known as the radar range equation for point targets. And it's going to be the principal equation that we use to be able to get a good handle on for design and other purposes when we're trying to do feasibility studies. If we want to see, for example, whether a particular radar system is effective for a particular application, this is going to be one of the main design equations we use. So, for example, if you were curious whether one of the radars we had in our lab was going to be able to detect a drone at 1 kilometer, you would be able to use this equation to get an estimate for what your received power is. And usually for detectors, there's the kind of rule of thumb that you want to have at least 10 to 13 dB of noise power, of signal to noise ratio. And so with that information, you can kind of do an initial feasibility analysis, for example, as to whether or not that would be an effective radar system or not for that particular application. As we meet in the upcoming weeks, we'll see some examples of that and work together on trying to use this equation. So this is kind of it for my video today. I wanted to kind of keep it short and sweet and give you an initial introduction. When we meet, we can go over some sample problems and see in more detail about how we can use the radar range equation. Take care, and I'll see you all later.